food. Yes. And yes, the thumbnail is Homer talking to talking to garlic bread from a Simpsons episode. If you haven't figured out, I like watching The Simpsons. I'm a big Simpsons fan. As well as Family Guy and a lot of other things too, especially like The Office. But yes, that is Homer talking to some garlic bread from a season, couple seasons ago, or something like that. Um, Questioning everybody to kind of get in here. It's off the screen a little bit. Again, this is geared towards eighth grade. This is geared towards eighth grade. Make sure my sound is good. Oh, yep, we're good. Okay. Again, this is geared towards eighth grade. Um, Hello. Um, those of you who had kind of hung with me with the other streams on that, I will kind of be repeating myself in the beginning here, but just to kind of reiterate, I'm going to be kind of going through some of information from the new packets that that will be going out on Friday. Um, there is the ability to access that early if you are so avidly inclined to want to access the packet early. If you go into Google Classroom, so if you go into Google Classroom and you go into classroom.google.com, and in this instance, in this eighth grade instance, if you click Fireball or Cosmic, so say for Fireball, and you get into this, you will see the post that is the same for every class. But you will see the post that is the same for every class. And I say here are the new packets I'll be referencing during my live streams. Please pay attention to what I'm going to be doing with the instruction during the live stream. And here in the Google Classroom, as we kind of go through the days and however long forward ahead, I'll be putting some little nuggets of information on there as well too to kind of help you through this. Um, but in this instance, all you have to really be doing is just click on that eighth grade BP. I just put the little 2 just because, well, that's the way I am. And you'll see everything come up. And what this basically is the information that we have, to the best of our ability, went through throughout the year till obviously the time that we've, you know, you know, the time that we've kind of, went all of our separate ways here. Um, but it's up to you. It's up to you. You want to access this early? Obviously, print it out. My suggestion here is to print it out front and back on your printer if you have that capability. Just because I don't think you want 38 pages of just one-sided. But reason it's such a big chunk is because as you see on this, you'll see that basically the problems are to the right side of the page, and the information and the quick kind of nugget of information is on the left. And so obviously each lesson, each part of this is going to take up a good chunk of the page. So I mean, when it really comes down to it, this really is not totally bad with this. You think you see 38 pages and you're like, oh my gosh, but really in all actuality, it's just kind of one side of the page. And a lot of this time, it's they're giving you word problems and stuff as well too. And again, this is supposed to last at the most 6 weeks. So if in the crazy instance we come back and we're back on May 1st or 2nd or whatever it is, we'll be able to kind of just step back into that where time got kind of frozen there on March 13th or yeah, Friday the 13th. Everything went down on Friday the 13th. Yeah, it's crazy, 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 crazy. But again, just to access this, it's Google Classroom. Google Classroom. You should be able to pick the pages. Again, I just have all 3 grades put to the same post. For you guys, it would be clicking the 8th grade. If for some reason you want to click 6th or 7th, obviously you are more than inclined to do so. With that being said, I'm just going to kind of go through a little bit of information here for you guys to just kind of follow along with what I'm doing. Again, we will kind of get more into the vocab review of this too soon. There's a lot of this that really is, very much, very much, very much important with this. So look at this. If you look at this, and it starts off with number one. Here's the first little nugget of information. Rational numbers is decimals. I will tell you, knowing what I know now and knowing what I know, how much this really caused a lot of issues. That's right now. Don't worry about that for the most part. Talk about that another time. That seemed to cause so much of an issue at the beginning. I just one thing I can that kind of hits into my mind there, and it's kind of like, oh my goodness. What I want to kind of focus with here is to focus with. Let's go to. We'll talk irrational numbers too another time, but so I want to go down to where it says evaluating square roots and cube roots. Now, if you look here, if you look, again, it gives you like a quick verbiage review and says, remember that a perfect square. So a perfect square is the square of an integer, any type of a defined number, numbers such as 2, 4, 6, 8, 11, 132, 2,135, 4,317. I'm just pulling numbers, pulling numbers out of the sky here, but a square root of a number is a number that when multiplied by itself is equal to the original number. So there's two parts to this. You have the square root, and then you have what we call you have the perfect square is the square of an integer. The square root is taking it the opposite way. And then you have the perfect cube, which is a cube root of a number, is a number that when cubed, multiplied 3 times is equal to that original number. So, what does this all mean? What's crazy is it gives you this whole litany of this information here. But in the instance of number one, I always like to break this down and say, well, the number 27, it's saying classify each number as a perfect square, a perfect cube, both, or neither. So I would always start in this instance in saying, well, let's go perfect square. Is there some number multiplied by itself that's going to equal 27? And you have to kind of go through. What's up, Mr. Nelson? So when you go through everything here, you have to say to yourself, what number times itself will give you 27? You start really running through it and you say, okay, well, 2 obviously can't go into it. 3 can, but here's the thing. 3 goes into 27 how many times? 3 goes into 27 9 times. So 3 goes into 27 9 times. Well, 9, we do it a different way here. The prime factorization. 27 can be broken down into 3. 3 times 9. 9 can be broken down as well. 3 times 3. Again, this is prime factorization. You're creating your tree. From 27. And you come to realize, well, 27 can be broken down into 3 times 3 times 3. And what is 3 multiplied by itself 3 separate times? That is what we call a perfect cube. 27. So 27 is a perfect cube. It's a perfect cube. So perfect. It is a perfect cube. That's a bad U. Okay, perfect cube. Now, with number 2 on this, and that's where prime factorization kind of gets a little bit in my instance, gets a little bit kind of wonky, because if you start sitting here and you're going, well, 100 can get broken down into 2. 100 can be broken down into 2 times 50, and then you start doing all this, and 2 times 25, and then it becomes 5 times 5, and and you kind of get into this, and it's kind of like, okay, it doesn't really work in that instance. You have to kind of start to be looking and saying, well, what number can go into 100? Well, 2 can, obviously. 5 can, but what about the number 10? So what about the number 10? 10 can go into 100 how many times? 10 can go into 100, well, 10 times. 10 times 10 is 100, or 10 squared is 100. 100 in that instance is going to be a perfect square. A perfect square. What this is all about is just kind of recognizing which one is a perfect square or a perfect cube. Now, in the instance of number 3 here, with number 3 with 64, this is just where you have to kind of know your factors, and you have to say, I mean, you can obviously sit here, and I'm going to kind of break this down. We say, well, does 64 have a square root? Does 64 have a square root? Now, those of you with, let me see if I can kind of bring this up. Those of you with your calculator, you can take 64 and you can take your square root. You can take your square root on this. I'm kind of showing this here. You see my light. But the square root of 64 is 8. So 64 is a perfect square. So 64 is a perfect square. But here's the thing. 64 can also be cubed as well too. The perfect square of 64 is 8 times 8, 8 times itself. Then the next part of that, the cubed root of 64, you can take the number 4 multiplied by 4, which will give you 16, multiplied by 4 again will give you your 64. The number 64 is a perfect square and a perfect cube as well too. Okay. So that would be your answer of both. Okay. Again, you can take the calculator and go through and do a cubed root of something and do a square root of something, and you should be able to figure that out. Like the instance of 24, is there a number multiplied by itself that'll give you the 24? And the answer to that is no. Cubing something, can you cube something to get 24? And the answer is no. So again, it's all about recognizing cube roots, square roots. What can you do to do that? And it's kind of what we were doing here with this next part, when it's like solving the equation using square roots and cube roots. And this is pretty much just kind of saying, like for number 1, you're solving for x. So if I have x cubed equals 64, if I cube something, if you remember me talking during the class, talking about taking that, that opposite, that inverse, taking those, those inverse operations to be able to, to find these answers. Like if we were to say, well, what's the opposite of, addition, subtraction? What's the opposite of multiplication, division? We'd say, well, what's the opposite of squaring a number? Squaring a number, you would say, take the square root, and then you would be sitting here and saying, well, the opposite of cubing a number is going to be taking the cube root. And if you remember from what we just did above, the cube root of 64, the way of kind of showing the work here, it's off the screen. What you're trying to show here, you're going to take the cube root of 64. Again, that is the proper way of showing that. You're basically, this is showing the inverse inverse operation that you're performing here. So the inverse of cubing something is taking the cube root, which will leave you with just x on that left side. It'll leave you with just x on that left side. So then you say, well, on the right, the cube root of 64, and those of you with calculators or remember from above, the answer to that is the number 4. 4, because 4 times 4 again is going to give you 64. Okay? 4 times 4 times 4 again is going to give you 60. Okay, let's continue on here. So if we say like with this, x squared equals 49, x squared equals 49. Again, the inverse of squaring something is going to be taking the square root. That's the inverse of squaring something. You gotta get used to that terminology of saying squaring, square root, cubing, cube root. And I know we were getting back into that towards that before we had left when we were talking about, you're talking about volume of figures and surface area of things. You got to take square and square root and all this kind of good stuff. And you see this terminology, as far as you go here. So again, the proper way of showing this, the inverse operation, is like that. That. It's taking the square root of both sides. So the square root of x squared is just x. And then the square root of 49, what times itself, what number times itself is going to give us 49. And you just have to kind of run through it and say, well, there's 1, there's 2, there's 3. You kind of go through it and say, well, the answer to this is the number 7. 7 times 7 is 49. So 7 times 7 is going to be 49. Okay. So 7 times 7 is 49. Kind of. And you look to yourself when you say number 3, x cubed equals 25. X cubed equals 25. If you're solving for x, the inverse of cubing something is taking the cube root. So you take the cube root. Again, that's the proper way of showing this. That's the proper way of showing this. Okay. The cubed root of x cubed is going to be x. So when you solve for x, you say to yourself, you go, well, what's the cube root of 25? The cube root of 25, it's just the cube root of 25. There's no real actual way. I believe it's a repeating decimal, my understanding. So the actual proper way of showing this when you're solving for x is going to be x equals just the cube root of 25. Just the cube root of 25. Okay. All right. A couple more here, and then we'll call it a day. Or 6:30. 6:30. All right. Last one on this part here. So we have a container has a cube shape. So cube. If you have a cube means a cube. If I draw a cube to my best of my ability, such a great drawing right there. The cube is going to have the same. So you have to look at this and say, well, the cube shape right here means that each of these sides are going to be the same. So it's basically saying when you find the volume, length times width times height. So that would mean you're taking that same measure of that side and cubing it, and it has a volume of 216 cubic inches. Cubed. Okay. What are the dimensions of one face of the container, of one face of the container, you have to kind of sit there and say, well, what is 216? What's the cubed root of 216? Okay. So in this instance right here, you take 6. Obviously, if you have a calculator that can do it, if you take the cubed root of 216, it's basically saying, well, what times itself again will give me 216. And your answer to this is actually going to be, if you do it on the calculator, if you're, I would suggest using the calculator, if you can do this part, until you get used to saying, well, the cube root of 100, or I'm sorry, the square root of 100 is 10, the cube root of 144 is 12, and you kind of go through the whole litany of things. Cube root of 216, so if you're sitting here and saying, well, what's the cube root of x cubed, and then the cube root of 216, it means that x is going to be 6. And you'll find out that 6 times 6 again is going to give you 216. Okay, so then the question becomes, keep this number 6, remember that number 6. It says, well, what are the dimensions of one face of that container? If it's a cube, that means it has the same dimensions for each of the faces. So 6 inches by 6 inches. It's the same. It's the same dimensions. Okay. That makes a little bit of sense. That makes a little bit of sense. Let's see what else we got here. We got my phone decides to mess up things here. There we go. Again, it's just recognizing roots, cube roots, square roots, all that kind of good stuff. Just kind of recognizing. Again, if you guys see this, take a look. Take a look at the example on the left side. Take a look at the quick review. It does get very, very verbal with a lot of things. That's where, use me as a reference point. Use these live streams as a reference point. Also use Google as a reference point too. When it comes to these, you just kind of flow through here. We'll get a couple more here on this last part, and then I'll bid you adieu. You guys remember the properties of the integers. It gives you all this nice little product of powers, power of products, quotient of powers. So what I really like to say on this is the A on this. So just for number 1, for instance, you see 6 to the 4th times 6 to the 3rd. What this is really trying to tell you here is 6 times 6 times 6 times 6 times 6 times 6 times 6. And I think I got it there. That's what number 1 is, what this is right there. So when you look at that, when you look at this and you say, well, how many times is 6 being multiplied? How many times is 6 being multiplied, by itself there? Well, you got yourself 1, 2, 3, 4, 5, 6, and 7. So instead of writing it like this, we use what we call the product of powers property in this instance. So we will add those 2 exponents, 6 to the 4 plus 3, which will be 6 to the 7. 6 to the 7. Okay. All right. And like with number 2 here, if you take a look at the power of powers property, it looks eerily similar to how this is set up. What this is telling you is you're having the base of 3 raised to the 6th power, and then you're going to multiply it by -2. You're going to multiply that power times -2. That's a There we go. 6 times negative 2 is negative 12, and you keep your same base. 3 to the negative 12th power. 3 to the negative 12 will be the answer there. Again, you can reference these to the left. Obviously, as you kind of see what's happening here, it's going nicely in order for you to kind of keep you going with this. So what number 3 is telling you, you have different bases. So different bases, 7 and 2. So different bases raised to the same power. So you have a different bases raised to the same power. You're going to take those two bases, 7 times 2, and then raise it to the third power. I'm just going right over here. Okay. 7 times 2 is 14. 14 to that same power. Okay. Finally, that last part, that's called the quotient of powers property. Again, they come up with some fancy names for these things, but when it comes down to this is telling you, let me clear the screen here, kind of scroll up as I kind of finish up with this here, the quotient of powers property. Same base of 4, raised to different powers. So you have the same base of 4 raised to different powers. You're going to subtract those exponents. So 4 to the 10 to the 10th minus 4, or you can look at it like this. 4 to the 10 minus 4 will give you 4 to the 6th as your answer. Okay. Hope that gives a little bit of explanation. That's about all I have on this. Again, any questions with anything? If there's any questions with anything, by all means, reach out via Google Classroom, reach out via email, all that kind of good stuff. Be happy to answer. With that being said, hope you all have a good day. I'll talk to you soon. Have a good one.